Hi everyone. Recently I've been working on a USB core for the ICE40 FPGA, and as such I had the need to debug some low-level USB signaling. And what I'd like to do here is present some of the options that I use to do that. This list is limited only to USB 2.0, so the low speed 1.5 megabit signaling, full speed at 12 megabits, and high speed at 480 megabits. Um, I'm also only considering passive audio captures, so no active man in the middle and no software-only solution like USB Mono on Linux, for instance. The software-only solutions, they often can't provide the required low-level details when you're trying to bring up something from scratch on a FPGA or on a microcontroller. They only become useful when things are at least half working. So let's get started. For our first option, we're going to be looking at the cheap USB analyzer. The things that you plug on USB. This is an official Celery one, but any Chinese clone or homemade ones based on the FX2 or any USB logic analyzer um, should work just fine. Now, this is streaming the samples in real time, but it's limited in sample rate. And this model in particular, and most of the FX2 based ones, are limited to 24 megasamples per second. And this is not enough to capture reliably USB full speed. So this method of capture is limited to the slowest USB mode, which is the USB low speed, which works at 1.5 megabaud. And this is a USB target that we're going to look at. It's an AVR Tiny 85, which is running the software USB stack for the AVR. And what I'm going to do is start a capture and plug it into this. And so this is a USB extension cable. This goes to my PC. That's the USB host. And that's just a tap adapter which allows to get access to the USB data wires, and then I run them, to the actual logic analyzer. So this is PostView. If you don't know PostView, you definitely need to check it out. I will put the link in the description. But it's a great suite of software. PostView and the associated project sigrok is what I'm going to be using to grab data of this USB logic analyzer and analyze the USB protocol. So first I'm going to connect to the device. Here, cellular logic. I already configured it, so I configured to only display D0 and D1 since that's the only lines I'm using. I'm going to capture at 6 megasamples per second because even if this can go up to 24, since we're looking at a USB low speed, it doesn't matter, 6 is enough. And I'm going to capture 50 million samples. So I'm going to start the capture, then plug the target in so that hopefully we can capture the USB enumeration process. And there we go. Let's see, we definitely captured some data. So now the major strength of this is the protocol decoders. So here you can add USB signaling decoding, and what this will do is you tell it which line is D plus, which line is D minus, that you want to decode low speed. I mean, it can auto detect, but I might as well specify it. And then above the signaling, you want to decode packets, and you also want to decode USB requests. And this will actually decode the USB traffic and display it. And if there is any error or non-compliance or stuff like that, it will display it. And so here you can see, all the packets that have been exchanged and figure out what went wrong and everything. And so, for instance, this is setup token, and then the data that's associated to that setup, and then it decodes requests. So this is an entire control transfer and the various transaction in it. And so, yeah, PulseView and the protocol decoder to analyze USB is a great tool. So that was our first option. We're now going to move on to something a little more advanced that allows us to look at USB full speed. So a quick rundown of the setup here. Again, here we have a USB extension cable that comes from the PC and serves as the USB host. We have the USB tab to easily access the data and ground line of the USB. But now we have a new target. This is just a random development board that has a USB connectivity, and it will act as a USB full speed device for the purposes of this demo. And finally, we have this board. This is what we're going to use to spy on the USB bus. This is an Icebreaker FPGA dev board by 1bit squared, and it has an ICE40 FPGA. And what we're gonna do is to basically use it as a logic analyzer, and in a way, it's gonna work as pretty much as the USB logic analyzer that we saw previously, but with a few important differences. First, it's optimized to only sample 2 IOs. So the previous ones, they always sample at the minimum 8 IOs. This will sample them at 96 megahertz, which means we can get an accurate representation of a USB full speed traffic, which is at 12 megabits. It has an internal buffer of 500,000 samples. And finally, very importantly, it does error run length encoding compression of the samples to save bandwidth. The project code that we're going to run on it is a project of mine called IUA that you can find on GitHub. So this is it. I will post the link in the description. It's mainly targeted at the Icebreaker or the Arduino ICE40 dev boards, but you can pretty much port it on, any ICE40 board pretty trivially. It samples the data and then sends them over a serial link. We have PostView again. I'm going to start a new session, connect to the device. So we have a special driver for this ICE40 USB analyzer that you can download and compile as well. Select the appropriate serial ports. Here, running it 2 megabaud. There we go, we're connected. We see the data lines. So what I'm going to do is start a capture, plug the USB dev board so that we can capture the enumeration process, and then we'll take a look at it. There we go. So yeah, I can see that I have definitely captured some data here. So again, take advantage of sigrok's protocol decoders, adding USB signaling with the appropriate options, GP, DN, full speed signaling, and then above that we want to decode USB packets, and above the USB packets we want to decode USB requests. So we can see it's processing in the background. Because this is capturing at 96 million samples per second, there's actually quite a bit of data to capture, even if you only have like 6 seconds of data. And if you do very long captures, it can actually take quite a bit of memory, so be aware of that. And there we go, we have some data decoded. If we zoom in, here for instance, yes, we can see classic enumeration procedure. This is control transfer. This is requesting a device descriptor, and so here we have the first transaction with the setup token, data 0. This is 8006 is get descriptor, 01 is device descriptor, and here we can see the device repeatedly knocks the request until it's ready, and then at some point it is finally ready to answer, and he answers with the data. 1 block here, and then we have the status stage of the transaction. The device knocks it twice and then finally acts it, and this completes the control transfer. And then we have a bunch of other control transfer, and this is the entire enumeration procedure. And if you had anything wrong in there, like if something, you're debugging your own USB implementation or whatever, full speed, you can see exactly what's going on the data lines, and when things are exchanged and what's going wrong. So another option to look at USB full speed is to use just a plain old scope, digital storage oscilloscope. In my case, I have an Agilent scope. I That's what I'm going to be using. So here's the setup again. Against the cable coming from the host, the USB tap. This goes to the same target as before, a USB full speed targets, just random dev board. And this time the probe is just connected on the two data lines and directly go to my scope channel 1 and 3. When trying to capture USB on a scope, the trickiest part is triggering, because in USB full speed you have those packets currently displayed on screen. These are starter frame packets. They come every 1 millisecond. They're very short, and if you try to trigger just simply on an edge, chances are you just kind of capture those packets instead of the ones you're interested in, especially if you're trying to capture the USB enumeration sequence. To work around that problem, one solution is to use advanced triggering features of your scope, and I'm just gonna show one way of doing this. Now it might not be applicable to your scope, but most modern scope will have some kind of equivalent features. Two things we're gonna do is first set up what's called segmented memory, segmented capture. So that means that the scope, instead of just capturing one entire buffer at once, it will capture several buffers basically. So here, let's say that I'm gonna capture 10 segments. Yeah. And the other feature we're gonna use is instead of simply capturing on an edge, we're gonna use something called nth edge burst or nth edge trigger. And what this is gonna do is, instead of triggering as soon as it sees an edge, it will need n edge before it triggers, and if it doesn't see any edge within a certain idle period, the counter will reset. And so here I've set it up to have an idle period of 1 microsecond. So if there is no activity for more than 1 microsecond, the edge counter is going to reset to 0, and then it will wait 25 edge to trigger. And because those starter frame packets are very short, they don't have 25 edge inside of them, which means it won't trigger for those packets. So it's all set up. So what we need to do is set up our time base correctly. I'm gonna go with 200 microseconds and start around here. Okay, so now I'm gonna disconnect the dev board, put the scope in run mode, so it's waiting to be triggered, and then I'm gonna plug the board and hopefully it will capture the enumeration sequence. And there you go, it captured 6 segments. It's good enough. Let's look at what it captured. So acquire segmented current segments, and so hey, yeah, we can see we definitely captured some traffic here. Now it's not perfect. You can see that some of the transaction we didn't catch them at the beginning, which can definitely be inconvenient. But if you play a little bit with the time base or do multiple runs or stuff like that, most likely you'll be able to capture what you want. That's what we have. I really don't want to decode that by hand, right? It's just annoying. Now my scope doesn't have a built-in USB protocol decoder, so what I'm gonna do is download the data out of the scope using the Ethernet port and import it into sigrok, into PostView. Now PostView and sigrok have drivers for some of the scope directly built in, and you can do that directly from the interface. It doesn't for that scope, so I just have like a quick Python script that I hacked together to download the data and load them. I'm gonna do that now and then come back with the data loaded in PostView. So here we are. This is the data, the raw data loaded in PostView. Now PostView doesn't have the concept of segmented memory, which means all the segments are just put one after the other, and you can't see the division between them. And if a transaction or a packet was cut off in the middle, the protocol decoder might throw an error at some point, and you kind of have to be smart enough to ignore it. Now, we can see the data, and we can see our packets, but this is analog data, and the protocol decoders, they want digital data. So the first thing to do is to apply conversion to them, and here I'm going to apply conversion via Schmidt trigger. It's going to be fine. Same thing for the other channel, conversion to logic via Schmidt trigger. And then we can see here we have the overlay of the data, the analog data, the original data, and then the converted to digital data. And so once we have done this, we can do the same thing that we did before. Add the protocol decoder, select D plus is channel 1, D minus is channel 3. Signaling, we're looking at full speed, and then we want to process the packets and then process the requests. And there we go. We have the same enumeration data that we looked at before. So if we look here, yeah, we have the setup packet, the data, the request descriptor, transaction, and then the device knacks and knacks several times and stuff like that until it finally answers. And then, yeah, so that's exactly the same transaction as we looked at before. But instead of using, the FPGA thing, we use the digital scope to do the actual capture of the data and then import them into PostView for analysis, which is, really, really powerful tool. And here you can even see some analog thing. Like if you have some signal integrity problem or anything like that, you would see it here as well and be able to debug that in this tool as well. So the last option I'm going to talk about today, and pretty much the only option if you want to look at high-speed traffic, which is 480 megabits traffic, is to use a dedicated USB protocol analyzer, basically. Now, one of the very common one is this one, the USB 480 Beagle from Total Phase, but as you can see, these things are pretty pricey. But there is actually an open source, open hardware alternative, and that's the OpenVizsla. It was originally a Kickstarter and some hardware was produced, but now it exists, and you can download all the hardware, all the software. You can make your board yourself, or recently you can also just buy some boards from the Sysmocom shop. So you have different options at different prices, but compared to the more than $1,000 price tag, $120 is pretty affordable. And so this is what I'm gonna experiment with today. So this is the actual board. This is the upstream port. This is connected to the machine that's going to do the actual enumeration and will see the device on the test. This is the port where you plug the device on the test. And for this test, I'm going to use just a USB key, which is a high-speed device. And this is connected to my laptop, which is going to do the actual protocol analysis. So let me just set the software up and let's see how this works. So I downloaded the software, compiled it. There is no fancy GUI or anything, it's just a command line utility. You can actually save the data and explore it in Wireshark for doing protocol decoding. But here I'm just gonna look at the text output basically, because at least for the kind of debugging I do, just seeing the text output and the raw packet data is enough for me. I didn't want to have to rebuild Wireshark with the plugin for this. So I'm just launching the control software, telling it I want it in stiff mode and I want to look at the high-speed traffic, and then I'm gonna save the actual output to a log file because it can be pretty verbose. So yeah, it's loading the onboard FPGA and then yeah, doing all of that. So now I'm just gonna plug in my device to test and see what happens. So it's doing things, and yeah, there we go. I think it's done. So let's look at the output. Yeah, here we can see, set up the same kind of descriptor request that we saw in the other cases, and here the response a little bit later, and all the protocol data and everything that goes on, and there you go. And so we can successfully capture high-speed traffic, and if we needed to analyze whatever, we could do it with this. And if we want to get fancy, you can also get the data, save it as a PCAP file, and load it in Wireshark and things like that. So yeah, if you want to look at high-speed USB traffic, this board is a great choice. So there you have it, a quick rundown of some of the options you have if you want to do some low-level analysis of USB 2 traffic. I hope you found it useful, and if you have any question or would like more details, feel free to ask in the comments, or even better, in the mailing list or IC channel of the relevant project. Thank you for watching, and see you next time.